Well, ladies and gentlemen, thank you so much for joining back. This is day two of technical sessions, Waste to Energy Gasification India 2021. And we are down to our last session. We'll be talking about novel technological and analytical approaches. And it truly is an honor to introduce to you the next presenter. He comes with a host of experience, and we're really enthralled to have Miss Dr. Makrand Gangrekar, Professor Environmental Science and Engineering, IIT Kharagpur. Despite all the advancements, the session will cover waste to energy technologies that will have a long way to go in terms of being on par with conventional energy sources. The session shall also focus a bit on new upcoming WTE technologies like hydrothermal carbonization, dendro liquid energy is a nearly zero waste WTE innovation from Germany. So, without taking any more time, I'll let the gentleman who has amazing experience in the field, Dr. Makaran Gangrekar. Thank you so much for joining with us, sir. I'll hand over the screen to you. And after sir's presentation, you can actually go ahead and put up all your questions. You can see on the right hand side.
Thank you, Mr. Ravin, for the introduction, and good afternoon, ladies and gentlemen. So, let me share my screen and then we'll start. Okay, Mr. Ravin, can you confirm the presentation is visible?
Yes, sir, it is visible.
And I'm audible as well, right?
Crystal clear,
Okay.
sir.
Okay, very good. So once again, very good afternoon, all of you, and thank you, organizer, for giving me opportunity to be here and interact with you and present the work mostly that we have done in the recent past, last decade at IIT Kharagpur. So today, in next 40 minutes, I will be presenting our experience of exploiting biological as well as bioelectrochemical wastewater treatment technologies to facilitate producing reusable quality treated water and resources recovery in many forms. So, ladies and gentlemen, we are all aware that the water scarcity and ensuring water security is a global concern. Our freshwater commodities are getting reduced day by day, and by 2025, we expect that the freshwater availability might get reduced to only about 5,700 meter cube per capita. So that is a matter of concern for all of us. And scientists from their level base, they are trying to patch up this gap and find out the alternative sources of water. Here we consider wastewater as a resource, and if we treat it properly, then we can get assured quality water supply for managing our water demand. Other than the potable water demand, definitely we can use this water. Even if we treat it properly, as other countries are using, we can even produce potable quality water out of it. But there may be a social stigma, so I do not want to get into that debate. But certainly, we can produce for non-potable purposes assured quality treated water. So for that, whatever presently we are providing primary and secondary treatment, we need to have tertiary treatment in place. Worldwide, the RO is being popularly used, but our focus at IIT Kharagpur is to find out other alternatives than RO. According to the Central Pollution Control Board, about 62,000 million liter of sewage is being generated in this country. So out of that, 30% is being treated. And last week, again, CPCB has come up with the fresh report, and they are saying though we have more than slightly higher than 33% capacity for sewage treatment in this country. However, only about 18% of the sewage treatment plant are functioning properly. So really, we need to look into the scenario and patch up this gap. And I'm sure government of India is serious to work on this. So the wastewater, when we talk about municipal wastewater, it majorly contains organic matter, nutrients, and suspended solids. So we are right now planning for removal of these three pollutants, majorly apart from the pathogens which are there. However, the concern that is getting shifted now is the presence of emerging contaminants. While utilizing water, we are using personal care products, Then antibiotics we consume, about 60% of that goes into the human excreta, and finally it joins into water body. And insecticides, pesticides, though meager use that we are doing it in house, so during subsequent floor washing, this also will appear in the municipal wastewater. So this is a concern, though at low concentration, many of these compounds are endocrine disrupting compounds, and hence they are matter of concern. We are aware that many areas in India are water stressed and spend huge cost on bringing water from the larger distances. And during the transportation and distribution itself, the 20% water loss occurs. So that open up a window that if the localized sewage treatment plant is being planned, then we can minimize this transportation cost of the water, and assured water will be made available for fulfilling many other non-potable uses in the locality. Like many cities in summer, we are not having water for maintaining greenery or aesthetic enhancement of the city, and then they get dried up. So at least this water can be made available, and many other uses for that matter. So a typical wastewater treatment plant comprises of a primary treatment, secondary treatment, and tertiary treatment. The primary treatment is meant for removal of coarser, settlable, means floating and settlable organic as well as inorganic solids. Secondary treatment is meant for removal of colloidal and soluble organic matter. And as per the needs, the targeted reuse, we need to have a tertiary treatment in place. Secondary treatment also talks about the sludge that is generated in the biological treatment. So that management also is involved in the secondary treatment when we provide it to the sewage. However, this secondary treated effluent will not be of reusable quality, and it needs further tertiary treatment for further removal of organic matter, for further removal of nutrients such as nitrogen and phosphorus, which is present in the municipal wastewater, further removal of turbidity to increase its acceptance, visible acceptance. The secondary treatment contains about 10 raised to power 4 to 10 raised to power 5 coliform number per 100 ml. So part of them are pathogenic, so that need to be reduced considerably, or rather fecal coliform should be brought to zero. Then removal of color and odor. Some there may be some residual muddy color, so that if organic matter present in a higher concentration, so that need to be removed. And because of the presence of organic matter itself, there is odor. And then now we are showing concern to manage to get rid of these emerging contaminants. Even at the low concentration of microgram per liter, they have the adverse effect. The National Guild Tribunal has come up last year with the recommendation of very stringent recommendation, ambitious recommendation. They have recommended that bring BOD to 10, TSS to 20, and COD to 50. However, we what we accepted, Government of India, is this standard for mega cities, class one cities, and capital cities in India. Though some concession is still given in some of the northeastern capital cities as well, and they typically follow the standard given in the third column. But days to come, we are bound to adhere with the standard, so that the water quality in the receiving water body can be protected, and then water can be used for recreational purpose. We are aware that many of our river stretch are not even, the water quality is not even safe to be reused for recreation. Forget about managing it for accepting it for potable purposes. So we need to adhere to these standards in the days to come. So the drawback of conventional sewage treatment plants, whatever we have, 33% capacity. So they require further, the effluent generated require further treatment for reduction of pathogens, removal of emerging contaminants, removal of nutrient or residual organic matter. Though they are bringing down BOD to 20 or 30 milligram per liter, but even that presence of the 20-30 milligram per liter of BOD or 50 to 100 milligram per liter of COD make water unfit for various other uses. And for municipal wastewater, typically the odor can be removed once the organic matter and the sulfur-bearing compounds are removed from that wastewater. So the currently recommended, as I was talking about RO, the RO is a proven technology. If we secondary treated effluent, if we remove turbidity further and then get it ready for the reverse osmosis, it will produce clear H2O. But that is a cost-intensive process. So we need to find out some alternatives In terms of cost, if I give you idea, many of you are having working professionals and having fair idea. So if I go for RO, then depending upon the size of the plant, it may cost me about 30 rupees to 50 rupees per kiloliter of the secondary treated effluent that I process through RO. So this will be 30 rupees addition over the primary and secondary treatment, which would cost around 7 to 10 rupees per kiloliter of the sewage that we treat. So this way, if we produce treated water with 40 rupees cost, so there will be less acceptance, and hence our major focus at IIT Kharagpur is to couple the mid and low energy consuming devices processes, so that we are able to produce wastewater at the affordable cost. So, for imparting sustainability to the sewage treatment, so that the reusable quality treated water can be produced to reduce the stress on the freshwater demand. In general, what we can explore is we can use algal based process, so that harvested algae can be used as a biomass for biofuel production, and that is being practiced in many countries in the full scale now, and even in India, many are researching, and few pilots have come up. We can recover electricity using the technology like microbial fuel cell that I will cover in my follow-up presentation. Sewage sludge can be explored for biochar, hydrochar, or such activated carbon production, which can be used back into the process for tertiary treatment, and surplus biochar can be sold to the other industrial application. We can explore anaerobic treatment technology for methane recovery. The treated water can be explored for aquaculture, so that will also fetch additional revenue. Or using the concept like microbial electrosynthesis, there is a scope to produce different synthetic compounds. And as I said in the introduction in the beginning, these technologies are still on the bench scale, and they will require some time to get mature. But scientists are working on it, and I will touch upon this during my follow-up presentation. So here onward, mostly I will be sharing the work that we have done at IIT Kharagpur. So we have USB-based flow anaerobic sludge blanket reactor type sewage treatment plant, which I constructed through project funding received from Department of Science and Technology and European Union. So this is designed for handling 400 cubic meter per day sewage. And one of the peculiar characteristics of this USB reactor, those who are aware of USB reactor, is while treating low strength wastewater, granulation of biomass is difficult to obtain in USB reactor. Whereas our USB reactor treating sewage generated on campus, so obviously we have per capita water use much more, and the sewage is diluted, and the average COD is 222 to 30 milligram per liter. So even treating such a low strength wastewater, we have two-thirds of the biomass present in the USB reactor as a granular biomass. So that is one of the indication of successful operation of the USB reactor. After USB reactor, the USB effluent is treated in the high rate algal pond. So high rate algal pond produce synthesized algae, and that harvested algae can be used for as a feedstock for biofuels. So these are still experimental basis that we are operating, and different value-added products recovery that we are exploring at IIT Kharagpur. So this is the performance of USB reactor. When we commission it, we unfortunately we started it in the winter, so it took a longer time for commissioning. But 2 to 3 months of commission time is normal even in summer. If we start to come up with the necessary biomass inside the USB reactor, it will take about 2 to 3 months time. So in our case, it took us more than 4 months time, and once it stabilized, it started giving 70% removal efficiency for total COD, and even in peak summer, we could touch upon a few days even above 80% COD removal efficiency. So we have in India about 40 plus USB reactor treating sewage, and most of them are struggling to give COD removal about 60-65%. BOD removal, they are giving 75%. Our plant is giving more than 80% BOD removal, and even in winter, the COD removal, total COD removal, is somewhere around 68 to 70%. So that is possible because of proper design and biomass granulation in the USB reactor. And in a way, we are able to recover methane. Right now, we are not. We are still working on it. This plant is in operation for 4 years. I'm trying to catch hold of some partner who can really utilize that methane with a low scale of 30 cubic meter per day for beneficial use. So right now, we are only flaring it with the flare stack. But still, don't have to spend energy for the treatment of the wastewater, and that makes this treatment economical. The role of high rate algal pond is to further give polishing treatment for organic matter removal and remove nitrogen and phosphorus, which USB reactor being anaerobic fails to do so. and then also it contributes for reduction of pathogens. So it produces effluent upon removal of 85% of nitrogen, more than 90% phosphorus, and 2 to 3 log scale reduction in the pathogens. It produces effluent with less than 30 milligram per liter of BOD, COD around 80 milligram per liter, and pathogens around 600 mpn per 100 ml. So this water is suitable to be used for restricted irrigation. I mean, where the human beings are not supposed to be in contact, it can be used, but it cannot be used for contact irrigation purpose, such as sprinkling lawns, where the people movement could be there. So then we modified the design. So further, to give polishing treatment, we set up about 300 cubic meter capacity per day modular sewage treatment plant comprising of a moving bed biofilm reactor, anaerobic and aerobic, so that the combination can remove nitrogen, then lamella clarifier, then dual media filter, followed by three-stage disinfection comprising of ozonation, ultraviolet disinfection, as well as chlorination as per the need. And then the final effluent is passed through the activated carbon filter to remove any disinfection byproduct that are formed. These are some of the photographs of the modular plant, and this is what the ambitious target that we had, that BOD should be nil, MPN should be nil, and treated water should be minimum committed amount is to 70, but we are able to get about 280 to 90 meter cube per day. So with this combination, and yeah, this is the removal efficiency that we obtained. So this is a better detail performance. So raw sewage, as I was saying, being in a campus and on the remote side of the campus, and a lot of academic area also in this stretch admit the water. So the sewage that we get is diluted. So around 189 average input COD. So final total COD is 23. Soluble COD is 12. BOD you can say less than 3. Sometimes we get, and at this low concentration, it is really difficult to measure BOD with the conventional method. Total nitrogen, we are successfully able to control it to less than 10. Suspended solid less than 10. Phosphorus less than 3. Coliform, sometimes we get accidentally 1 or 2 coliforms, but that water is really safe because fecal coliforms we are not getting it anytime. Surfactant also it is effectively removing. And what is more important is total organic carbon is 7 to 9. So this water is really safe, and this quality is much better than the water quality available in many of the natural river stretch, which we are accepting it as a raw water for potability purposes. So this concept we further moved it to the package treatment plant of 3 cubic meter per day. So what we did here is, instead of lamella clarifier, which is bulky, we replaced lamella clarifier with the membrane bioreactor. So combination of aerobic MBBR, anaerobic MBBR, and membrane bioreactor. So a compact module that we prepared that also gives more than 90% COD removal efficiency, close to 96% BOD removal efficiency, and even total nitrogen removal efficiency around 80%. MPN without disinfection, it is bringing it down to less than 300 MPN coliform per 100 ml, and even surfactant removal is also effective. So this package treatment plant is also effective to produce the treated sewage to meet the NGT recommendation. But if we want to reuse it for human contact purpose, some moderate disinfection by addition of bleaching powder can be done to produce water safe to be used in horticulture. This is the costing of this plant. This plant took us package plant 3 cubic meter capacity, 2.16 lakhs as a capital investment. Operating cost it has 5.6 rupees, and considering 15 years life of the reactor, the capitalized operating cost comes around capex rupees 21 rupees per kiloliter. So because of the smaller size, it is little costly. The return of revenue is also depends upon the water tariff. Obviously, if the water rates, as in many of the metro cities in India, they are more than 15 rupees per kiloliter. So definitely there is a revenue return. But if it is less than 10, then obviously there is no benefit if the water charges are less than 10 rupees per kiloliter. We extended this concept on campus to 1.35 MLD sewage treatment plant to manage the wastewater generated from the hostels. And there the target cost that our institute authority gave us is rupees 15 per kiloliter. And these are the plans. So after screen grit, we have anaerobic MBBR, aerobic MBBR, then lamella clarifier, dual media filter. Then it goes to the disinfection tank where we have arrangement for ozonation and chlorination. UV we have avoided because from 300 cubic meter plant we found that the UV is not playing much role. So ozonation and chlorination are better. This is the photograph while construction, and this is the photograph when the plant is put in construction is complete and put in operation since September 2020. And since then, the plant performance is still improving. So this is at the end of October. The performance of the plant, you can see the total COD is brought down to below 20. Soluble COD is less than 10. TKN also less than 10. Phosphorus also less than 10, less than 7. So we need to further improve this, and we expect with the more biomass developing in the MBBR, further polishing will occur here, or we might have to add some polyelectrolyte dosing to meet the requirement of 1 milligram per liter of phosphorus. Uh, TSS also less than 10. And right now we are only dosing ozone, so we are experimenting with ozone. So obviously, with addition of chlorine, this 300 MPN also could be a problem could be solved. So then we went on for estimating life cycle costing for 300 cubic meter and 1350 cubic meter capacity treatment plant. The cases that we consider is up to secondary treatment. So up to clarifier is the case one with the secondary treatment and tertiary treatment of ozonation. Then the case three, ozonation followed by chlorination. Case four, chlorination followed by UV, because presence of chlorine in a UV, it generates much more radicals and more effective in removing some of the xenobiotics compound. And then case 5 all in place, so ozonation, chlorination, and UV all together in place. And we estimated costing for both the plants, considering realistic lifespan of feed pumps, blowers, the replacement of the media required. So within 2 years, activated carbon will be replaced, even MBBR media. Then painting of the reactor every 2 years. So all cost, including contractor profits, analysis cost, depreciation cost. So we estimated these numbers. So I'm not going to detail, but what is important is the this. So this life cycle costing tells us that if we have only secondary treatment in place, then the major cost is the operation, is manpower cost, and then the capital component, and then comes the energy cost. Whereas when we have tertiary treatment in place, then obviously energy need booms, and that cost about 40%. Then 30% is manpower cost, and then less than slightly 30% is the capital cost for the plant. And then the remaining costing is operation and maintenance component, that is routine operation maintenance, analysis cost, third party analysis cost, and then the contractor profits. So and then these are the numbers. So for 300 cubic meter capacity plant, considering the installed capacity of the electrical components like aerators and pumps, so our treated water cost is coming about 16 rupees per kiloliter because of the small size. So when the same we extend it to 1350 cubic meter, we are able to produce water less than 11 rupees per kiloliter. And this water is really having quality safe. I'm not saying it for potable purpose because it still contains some of the antibiotics in traces, and hence, as a scientist, I cannot certify it as a potable water. But I can certify that if anybody by any mistake drinks that water, nothing will happen immediately. So, but long-term exposure is not good because of the traces of antibiotics present there. Now here I will start upon our research work on the bioelectrochemical processes. So those who are aware, it may be repeat for them, but those who are new, microbial fuel cell traditionally consists of two chamber, anodic and cathodic chamber, where respective electrodes are housed. So in the anodic chamber, the wastewater to be treated is admitted. So that anode provides the surface over which the electrogenic bacteria will grow. The electrogenic bacteria, when come in contact with the organic matter, it will oxidize the organic matter and generates electrons and protons. These electrons are taken through the external circuit over which the device that we would like to power is attached. Through this external circuit, the electrons are traveling towards cathode, and the membrane which separates these two chamber, traditionally proton exchange membrane, PEM. So this PEM allows only proton to pass through, towards anode. It should not allow the oxygen, which is typically this cathodic chamber is aerated. So the PM should not allow oxygen to cross over, otherwise it will directly consume organic matter for aerobic oxidation. Also, it should not allow substrate to pass over to the cathodic chamber. So that is the properties of PEM that is expected. So Nephon or Ultra-X, they are the popularly used PEM. So in a way, the organic matter containing wastewater is working as a fuel, and in turn we are able to recover electricity for certain on-site application. Depending upon the calorific value of the fuel, when we are using wastewater, obviously it is a low calorie material, so the electricity harvested will be low, and it could only be exploited for use for powering low power devices such as mobile charging or LED bulb charging, and this kind of low demand electrical appliances can be easily powered using this technology. So the advantages of bioelectrochemical system is a general umbrella generic name. So the BS have advantage as a sustainable green technology for wastewater treatment and generating electricity without any noise and without any additional pollution. Rather, it is carbon neutral because we are not using any fossil fuel. So we are generating electricity using organic waste, converts chemical energy stored in the organic matter, chemical bond of organic matter into electricity. High energy conversion efficiency, bacterial mediated reactions are expected to have high conversion efficiency, though in reality it has a challenge. I mean, we are not getting more than 40% conversion efficiency, while in the small lab scale controlled reactor, the conversion efficiency may go up to 80%. So electrochemistry and all those things are challenge, and scientists are working on it. Operated efficiently at ambient as well as low temperature, less sludge production, so excess biomass generation is less. Do not require any off-gas treatment, and no energy requirement for aeration as required in the conventional MFC if the cathode is made as a air-breathing cathode. It can be exploited for bioelectricity recovery. It can be exploited for biogas and hydrogen recovery. So we can configure the system to get hydrogen by imposing potential on cathode, or imposing potential on cathode. Even methane can be recovered. Then it can be used for metal recovery. It can be used for nutrient recovery. It can be used for phosphorus and even iron recovery, as reported by Cheng et al. However, there are bottlenecks and challenges that since the bacterial mediated electrochemical reactions, electrochemical losses are unavoidable. So there is a activation loss, there is a concentration polarization loss, there is ohmic loss while the charge is getting transmitted through the medium. So we need to minimize this as much as we can so that the maximum energy output can be obtained. Scaling up is a typical challenge because a single MFC can maximum generate, even using best configuration, can generate zero point 0.6 to zero point 0.7 volt, because theoretical voltage is 1.1 volt, and these laws put together will contribute, depending upon the properties of the material component used, about zero point 0.3 to zero point 0.4 voltage will be lost in the process. So zero point 0.6 to zero point 0.7 volt by single MFC. So we need multiple MFC in stack. So, and then there are challenges because of the stack, because of the reversal of polarization potential. So that will impose adverse potential on each other. So these are all challenges of operating this system. Expensive electrode accessories and costly separator, the Nephon and Ultra-X, which I was telling. The Nephon costs typically about 1,800 US dollar per meter square. So that is where it hinders the cost, and the production cost of this device will be 10 times tenfold than the conventional wastewater treatment technology. So here we chipped in IIT Kharagpur, and we came up with the clayware ceramics. So if the clayware, while baking, if we modify it with 20% montmorillonite, so it gives us similar proton exchange capacity as the Nephon is giving, and at much lower cost. So my cost of production of this ceramic membrane is less than 50 rupees per square feet. So yes, obviously I cannot manufacture it more than a square feet because of the brittle nature of the ceramics, but at much lower cost, and then I can use panels, as I will show, on the reactor. So this way the cost can be minimized, and actually it has worked as a breakthrough. And now UK company and one of the company in Israel, they are using these ceramic membranes and further installing the demonstration plant. Then the pH imbalance, like any other biological reactor, this is a issue. The current fluctuation will also be an issue. High maintenance cost expected for this reaction could also be a challenge because of the costly component of the material involved. However, it has various application in the field of life sciences. One of the application is, of course, wastewater treatment. It can be used as a BOD sensor. This has already been commercially marketed, MFC-based BOD sensor. It can be used for removal of hydrocarbons from polluted sediments. So you insert anode in the deep sediment, polluted sediment, and then have a cathode on the surface of the polluted water body. So in situ remediation of the sediment can happen. It can be used for generation of power from sediment MFC. So this is actually working in the Europe now. They have for powering the environmental sensors in the deep sea. So they are utilizing this power with MFC-based sensors, and we experimented at IIT Kharagpur in the aquaculture experimentation pond. So we installed anode in the sediments and cathode in the overlaying liquid, and in situ remediation of the aquaculture water without the external recycling was feasible, and the water quality can be maintained for a long to get desired success yield of the fish yield in the aquaculture pond. BAS has the potential to provide long-term, stable, and low power for biochemical devices that we implant in the human body. So even in the robots that it can be implanted, so to have the robot will feel himself when the potential goes down. So it can feel that it is hungry and it will eat the sugar cube and power itself. So that way it can be exploited. It can be used for rapid detection of the food contamination. It can be used for sludge degradation. So our experience in our lab tells us that the MFC based sludge digester requires half of the time as required for the anaerobic digester. It could be used for simultaneous secondary and tertiary treatment of the wastewater. So, organic matter removal as well as desalination. If we configure the system, that also I will share. So that is possible. Simultaneous wastewater treatment and desalination is possible. Synthesis of organic compound using CO2 as a source, that also could be made possible exploiting this bioelectrochemical system, configuring the bioelectrochemical system accordingly. So same thing in a pictorial form is shown here. So this will tell you the how scientists are paying attention. I mean, so far, when we started research in 2004 at IIT Kharagpur, there were only 21 paper around available. So at this stage, we jump in, and right now, nearly 13,000 publications are available addressing different issues, and this is where we are in this domain of microbial fuel cell research. So we are second all over the world from our group after Logan from Penn State University, USA, and then these people from UK, and then again Canada and Chinese people. Institute wise, we are in the fifth rank for contribution in this domain out of 13,000, nearly 30,000 papers. So we could contribute from IIT Kharagpur more than 200 articles addressing different issues of microbial fuel cell. And then, based upon the decade of experience working on the different component, we could come up with the 1,500 liter capacity on-site sewage treatment facility. So what we named it as a bioelectric toilet. So there is a toilet and there is a MFC-based treatment system. So this comprises of a central chamber. So this photograph shows in the horizontal to imagine it better. So this in reality it is placed vertical like this. So it consists of central chamber where the waste from the toilet is coming in, and then the liquid flows through this peripheral six chamber. So this peripheral chamber contribute further polishing treatment. So half of the liquid flows anti-clockwise, half of the liquid flows clockwise, and finally it comes to the final chamber where it is operated as an aqueous cathode along with the central inlet chamber. And we are dosing here hypochlorite. So you can see this hypochlorite dosing arrangement, and that generates the treated water. So as and when the toilet is flush, the waste is coming in, and then it is getting treated in this chamber within a retention time of a day or day and a half. So 1 to 2 days, as what the retention time is same as the septic tank. But we are able to produce treated water, which is safe to be reused for any purpose. Of course, from electrochemistry point of view, we have used a different catalyst to gain the advantage, better anode potential as well as cathode potential. But these are all low cost material that we have used. And this is the performance under different flow rates that we operated. And we found that when it is operated for less than 0.5 kg of COD per meter cube per day, so obviously we are getting treated effluent with less than 20 milligram per liter of BOD. So this is the variation that it has shown over the seasonal variation. Obviously, in the winter, the biochemical reaction rate lowers down and its performance slightly drops. In summer or any hot weather, definitely we get much better performance. Then this electricity, okay. This is the treated water characteristics. So BOD is average BOD is around 23 plus or minus 7. COD is less than 80 and MPN is less than 100 MPN per 100 ml. So this water is suitable to be reused back in toilet for flushing. So using solar power pump, we are pumping it to the elevated reservoir over the toilet. So the concept is in a remote area where people are reluctant to use toilet because of the filthy nature of the toilet. So if we make this kind of arrangement, so once the overhead tank is filled, so then every time people do not have to carry huge quantity of water for flushing the toilet as well. So they have to carry 1.5 liter only for cleaning purpose, and the toilet when it is flush on site, this is getting treated, and the solar power pump is pumping it. So in a process, the evaporation loss that is happening, so that is getting compensated because in India we use water for cleaning. So every use of toilet is about a liter water when the user is using. So that will compensate the evaporation loss. So this way, perpetual water use toilet, so free from any external supply of water, free from any external supply of electric grid, and in process we are generating electricity. So that is the biggest advantage. So that electricity can be used for illuminating the toilet premises and cabin at night. Also, the smell problem near toilet is eliminated because using this bioelectrochemical system, the ammonia is getting oxidized. Bioelectrochemically to nitrogen, so there is no ammonia smell, and sulfide is also getting oxidized to elemental sulfur. So our students are working whole day nearby this toilet, so there is no smell issue there. The sludge also has a better characteristics. So C by N ratio close to 20 we need. So around 18 we are getting. So sludge also has a good value, and we are further characterizing it for presence of pathogens in it. But upon drying, then it can be used as a soil conditioning agent. So this is the photograph showing how the toilet premises can be illuminated at night using the electricity generated by this BS. And there is one. This is two LED electric bulb and two LED. 2 watt LED bulb in the toilet cabin. So that is good enough to illuminate even the cabin at night. So this way, fearless use of toilet by the children and ladies can happen in the remote area where they are fearful because of the suspicion of the animal or insect attacks. So that way, this technology can work. But the only thing is the cost. This FRP based system is costing us about 2 lakhs, but when we make it with the ceramic cylinder, it cost only about 40,000. But then the drawback is the brittle nature. So by any chance, if anything strikes, then that cylinders may get broken up. So that need to be properly protected from the animal attacks. The dogs or whatever cats should not jump on it. And this is the electrical circuit that 500 farads, four capacitors that we are using to store the power. And when it is required, when the bulb is made on, so these capacitors get removed from the charging phase, and then in a series they start discharging, so that generate adequate power to illuminate these LED bulbs outside the premises of the toilet and inside. Looking at this success, then NTPC Netra campus, Greater Noida, they contacted us to replicate this, and we have installation at their guest house in the Greater Noida campus of NTPC for treatment of the wastewater generated from their guest house. So there we saw successful operation also. For 1.5 year nearly, we operated using further different catalyst on the electrodes. But the wastewater has a very strong characteristics there. I mean, because the on-site generated sewage was only used, so exorbitantly high COD we got. Though still it handled giving about 80% COD removal efficiency, but produce effluent with 300 milligram per liter of COD. So further polishing treatment is required for facilitating reuse. But if the inlet is diluted, then obviously these values can also be diluted, and reusable quality treated water can be produced. As I was telling, these microbial cells could be configured as a microbial desalination cell, so facilitate electricity harvesting as well as TDS removal, the desalination. So this, instead of two chamber, now we can make it a three chamber arrangement. So here the organic content in the wastewater can be oxidized, and then here in the central chamber we can have the saline water we can admit to have desalination, or same wastewater, if we have interest to desalinate, can be admitted. So because of the charge difference here, the anions will start migrating towards anode, cations will start migrating towards cathode, and this way desalination of the water can also be achieved. So we had a project sponsored by Tata Steel to Jamshedpur to treat their wastewater, and using five chamber desalination cell, we operated the performance, and with the different salt concentration, of course, with the higher salt concentration, the internal resistance of the system reduces, and that gives better performance. So for their industrial wastewater containing phenolic compounds are not that easy to degrade. So still we could get about above 80% removal efficiency, Coulombic efficiency, that is electricity harvesting efficiency, about 14%, salt removal 78%, and the power generation of this device around 17 milliwatt per meter square that we could obtain. The microbial electrochemical systems could also be configured as a microbial electrosynthesis system. So instead of harvesting electricity here in this case, if we impose about 0.5 to 1 volt on the cathode, then using carbon dioxide as a carbon source, there is opportunity to synthesize the organic compound. So it can work as a carbon sequestration system. What was our target here is the biogas that we generate. So biogas, we wanted to pass through this cathodic chamber, so that the carbon dioxide from this biogas could be captured and converted into valuable products, organic chemicals. And this way the biogas reforming also means enriching biogas in the methane content can also be possible. So this way, if we synthesize chemicals, it does not require any arable land to produce biofuel, and we are able to produce fuel or any synthetic chemicals as per our need and as per the imposed potential, or the catalyst that we are using on the cathode. So the philosophy is again simple, because the CO2 to other hydrocarbon compound, that it cannot be a spontaneous reaction, and to divert make that reaction happen, we need to impose potential. And using the acetogenic bacteria or other mixotrophic bacterial culture, we can synthesize different organic compounds in the cathodic chamber using carbon dioxide as a source. So it could be flue gas, or it could be the CO2 from the biogas. So when we operated a lab scale reactor, we could get acetate. These are the results reported by the other researchers. In our lab, we could get acetate, isobutyrate, propionate, piperidinone. So these are the compounds when we impose zero point 0.9 volt potential on cathode, we could obtain, and these are available in the public domain. Then we scaled it up to 12.6 liter capacity, very near to the USB reactor, where we continuously fed the small fraction of the biogas through the gas line. And using different imposed potential, we could go up to 400 milligram per liter concentration of acetate production in this reactor. So in a way, the biogas was getting reformed, getting enriched from 60% to 70% methane content in the biogas at the outlet, and this carbon dioxide was converted into acetate production. So this way also, even scientists have reported even ethanol production from this device. Acetate, butyrate, isobutyrate, ethanol, so that can be produced. We are working on to optimize the zero point 0.3 and 1.35 MLD sewage treatment plant. Basically, the further we identified some scope to reduce down the cost of operation as well as the capital cost. Then we are looking forward and open for translation of the results obtained from the two full-scale plant to prepare operating. We already prepared the operating guidelines and enthusiastic to replicate it elsewhere for benefit of the society. Further research on automation of this technology, the remotely controlled system, real-time monitoring system. So that is the research that presently we are engaged with, so that assured quality treated water at any given time could be supplied to the individual. Then looking forward for knowledge dissemination, for enriching public outreach, providing knowledge-based support system toward the interested government and non-profit organizations. We would like to undertake the research further to reduction in the cost and operational redundancies for the future applications, and producing trained manpower for operation and maintenance of STP in general. So this is our research group, the set of young people who are working hard to make me possible to have the presentation in front of you. To credit, all credit goes to them for the data that they generate. And thank you very much for your patient listening, and save water for secure future. So thank you everyone. I'll be happy to take a few questions if anybody has.
Thank you, Dr. Gangrekar, for that insightful presentation.
I hope I am maintaining my time. Yeah,
Sir, absolutely on time, on point.
thank you.
Any questions from the audience? If you have, you can go and write them down in a Q&A tag. Also, if you would want to ask Dr. Gangrekar question one-on-one on face, please raise your hand and I will pull you up on the main screen. In the meantime, we get some questions from the audiences. Doctor, I curiously wanted to understand this from you. So, all these novel methods that are coming in right now, in terms of getting our attention towards the fact that the planet needs more caring, what do
Yeah.
you see in the coming decades, the way forward? What are the approaches that are just theoretical right now, but might be an option? Is there anything in your mind right now like that?
See, having a researcher in the bioelectric chemistry domain, I would emphasize that the technology has a potential, but there are limitations as well. I mean, as you correctly said, that the planet need care, and we need to find out the technology. Right now, the technology that we are using for wastewater treatment, I'm restricting myself only about the waste management part, but there are opportunities at other places as well. So they are energy intensive. I mean, instead of generating anything, so we are putting on energy for treatment of the waste. So if we properly devise the technology, so they could become the waste could become a resource from where many valuables can be harvested. So that we should try. Though the stake, when we talk about the energy sector, the stake may be 10-20%. The energy harvested from the waste definitely is not going to fulfill entire our energy demand, because even if we divert our entire food for energy production, the energy that it will generate is only about 100 to 200 watt. But every individual, we consume about 2 kilowatt power, even in the average Indian scenario, 1 to 2 kilowatt per day that everybody consumes. So that is not going to meet. But still, if we manage this 10% stake, 10 to 20% stake, still at least that will reduce the fossil fuel footprint, and that will help the planet in a bigger way. That's my perception, but I'm open for any comment or any exception.
Uh,
There is a comment of MES how to control the process parameter. Definitely, when we use pure culture, we get much better result. But in the reality, this is a question from Mr. Prakash Thanki. So in reality, in the real life, maintaining a pure culture would be impossible. I mean, it's bound to get contaminated while exposure to the real environment. So what is the best strategy is to, what I recommend is a bio augmentation. So instead of relying on a pure culture, have a mixed culture which is augmented with electrogenic bacteria. So this way we can get much better result. And my lab as well as other scientists working have reported about 40 to 50%, or even 60-70% energy conversion efficiency has been reported by other scientists. But to be frank, in my configuration, we got about 45% energy conversion efficiency in a lab scale, that is 2-liter scale reactor. When the same reactor I scale it up to 700 liter or 1500 liter, as I said, so then the energy capture goes down to 6 to 7% because of the electrochemistry limitation. The material that we are using, it is not capable to handle that much of current density. So this is where we need to look at the composite material, which is capable to handle more than 5 ampere per centimeter square of the current density. So this is where I'm struggling. I'm not finding a material. Normal carbon material that we use cannot handle this much level of current density, and that is why the energy capture is less. I hope I'm able to address the question.
Thank you, sir. There's an added-on question from Prakash ji. Can you,
What could be the reason in India we are able to install anaerobic digestion?
as a matter of fact, Prakash ji would just ask me to get him on the screen.
Sure, sure. I'll be happy.
Uh, uh, Thank you very much, sir, for presenting it. Actually, it is a typing error. I'm questioning is that what could be the reason as India is not able to install that much anaerobic digestions in a sewage treatment as well as a different wastewater? Because main problem, as you rightly guided to us, that we are not able to put this anaerobic digestion, although we are need to put energy to put the oxygen to the bacteria and then bacteria will convert into carbon dioxide and all. Instead of we should do first convert into energy, then that energy should be put into like leftover part of the organic material should be converted into aerobic products.
Absolutely. Absolutely, but some of the places where the municipal wastewater also receives, say for example, tannery wastewater, means depending upon the component, if it is a sulfate-enriched wastewater, then the anaerobic treatment may not be good choice, because during anaerobic process, the sulfate will get converted into sulfide, and the oxygen problem still persists. The effluent of the anaerobic reactor will still have oxygen demand. So I would not recommend such high sulfate-bearing wastewater anaerobic process. Though I am myself is a IWA member to promote anaerobic digesters in South Asian countries. But such wastewater is not suitable. But normal municipal wastewater, the sulfate content is around 80 milligram per liter or 100 milligram per liter, whereas COD is 300 milligram per liter. So there I would recommend anaerobic digester, but not for the wastewater where the like in Kanpur we have around 500 milligram per liter sulfate, and then similar magnitude COD. So there it may not be best choice.
Oh, okay. But then also, sir, why it is not putting up the even I have asked the same question to even the big companies, technical peoples. They said one constraint would be land constraint, but whatever it may
It,
be,
it
like
require
people
it,
say
it require rather less footprint with the USB reactor, much lesser
that,
footprint that it
that
require.
no, people consider SBR and MBR as a efficient treatment, but in that case, we are need to investment would be very high. The energy cost consumption should
Yes,
be very high because we need to put oxygen. Whatever the organic concentration is there, we need to convert into carbon dioxide and water.
absolutely.
So, and MBR is
SBR based
again a
plant,
cost.
SBR based plant require 1.5 times the investment than what I showed you the MBBR type plants which I have on campus.
So why, sir? Particularly, why this particular thing is not thriving in Indian market? Because it is thriving in a European market where they need to increase, they need to maintain the energy also. So
Uh,
that is like
what I
quite.
feel with the over enthusiasm, the PEX India initially 2 decades back started marketing in India, but they failed to fulfill their commitments, and because of that, people are skeptical. Looks like, whereas the SBR, Citec or other companies, when they jumped in the India, so now the largest the SBR based plants are there in India right now, whereas a decade back there was not even a single SBR in India. So now the India is a major player in the, so it is a marketing strategy of the individual company also that is driving, and that is convincing the other people. I feel so, because one failure associated with the anaerobic reactor, people are still skeptical whether it works or not. But I have a demonstration plant and which is working for 5 years, absolutely fine.
So in that case, we can consider it as a more towards the skill on mindset of the people. As one
Right.
plant is not working, it doesn't mean that everything will not work, right?
Exactly,
We should
exactly.
not stop our.
We should identify what is the root cause of failure and try to fix it rather than
True.
blaming it to the technology.
True, sir. Thank you. Thank you very much, sir, for your
Thank
answer.
you. Thank you for your interest. You're mute, Mr. Ravin.
I'm sorry. I've been telling everyone to unmute themselves and I have muted myself. Okay, so Dr. Ghangreka, thank you so much. I think that wraps about the Q&A session as well. It has truly been an honor to have you here, and thank you so much for enlightening us on all the opportunities that lie behind the horizon. And I'm absolutely sure that you will continue doing this amazing work, and we seriously look forward to seeing you again next year.
Thank you, Mr. Ravin. It was pleasure interacting with you. Thanks for giving me opportunity to present our work. Thank you.
Thank you so much, Dr. Ghangreka. So that, ladies and gentlemen, is the end of our sessions, the technical sessions, waste to energy. And I would like to thank once again Professor from IIT Kharagpur, Dr. Makaran Ghangreka, for being here with us and giving us those valuable insights. And with that, ladies and gentlemen, I would open the floor to any one of you who would like to give out anything on the on the 2 days of gasification India 2021. If you have anything to say, if you have any thoughts, the whole experience of being here with us, I would be very happy for you to raise your hand, and I would bring you up on the screen. So I can see a few people here. Right. Mr. Vijay Yelaga, if you have any thoughts on any words on your experience of being a part of Gasification India 2021, I'll be very happy to pull you up on the screen. Okay. So just a quick reminder that this has been a virtual event, and we actually understand this year has been a difficult year for a lot of people because of the pandemic. But next year, hopefully, we'll have a better reach with you all. We'll be very happy for all of you. Mr. Dalvi is going to be here. I would be very happy for Mr. Dalvi to take the center stage and give us a few words. Mr. Dalvi, over to you.
Yes, thank you very much, Sri Ravin Kundu Saab, and I'd like to, with folded hands, thank Dr. Gangrekar Saab also for an insightful presentation. Sorry, I was giving a vote of thanks at the other session on gasification, and it's too much technology to confuse, but still we are on version 1. But hopefully, next year, God willingly, everything goes well. We don't have the pandemic third wave, and I can assure you, on behalf of our Director General Shri Ashwin Kumar Khatri, that we'll meet up personally, physically, if things go well, at a 5-star facility, primarily either the Taj Vivanta New Delhi or the Taj Palace New Delhi, where we can actually interact in person. So I'm sure many of my sponsors, a special thanks to Avantgarde, Sri Ilongo Saab, Sri Gladstone Sir, and also to Aquasource Technologies. We have the representative in India, Desai Sir, and also Dr. Digge for supporting the conference. I remember my journey with Waste to Energy and Ashwin Kumar ji goes almost 10 years prior, a decade back, where we had done our first conference on waste to energy. And I remember we had approached the then prominent scientist and our beloved President of India, late Dr. APJ Abdul Kalam sir, who had actually mentioned that India needs to be less dependent on fuel, but more dependent on biofuel. And there will be a day when our planes will fly on biofuels. So that was Dr. Kalam's vision, the legend. And with that in mind, Ashwin ji also shares the same vision. We have been approaching Niti Aayog, and I can assure you that this is not just a conference where we meet, we greet each other, say goodbye, and we forget each other. No. We will be taking a collective voice of the industry, Dr. Gangrekar, that's an assurance. And for all the audience who are present here, I'm sure Sundar Alango sir will also appreciate the fact that we are doing this endeavor, that even after the conferences, we will be taking a collective voice of the industry, send the videos and the periodicals to Niti Ayog, Dr. Saraswat, Dr. Amitabh Khan Saab, whom I know personally, and of course to the varied ministry. I remember I used to go to the lobby of MNRE, that is Ministry of New and Renewable Energy, when our good old friend Dr. Prakash Javadekar sir was there. But there has been a lot of changes over the years. I mean, our Honorable Prime Minister Modi Saab's cabinet is also shuffled with a lot of new union ministers joining. I remember me and Ashwinji had invited them, and in spite of their absence, they have mentioned that they are keeping a close watch on these conferences, and they will see that many of the issues will be sorted. A very heartfelt thank to Punjab Renewable Energy and a presentation from Colonel Sumit Malhan Saab. I was wondering, Ravin sir, if any of the participants among the audience would like to share their experiences, and if they can press the raise hand buttons on the screen, any of their experiences, what they expect. I do understand this is a virtual conference. Maybe next year when we meet physically, if there are any expectations, Ravin sir, what I would suggest is please keep the sessions open so that they can share their feedback to the organizers, Mission Energy. With this, on behalf of Ashwin Kumar Khatri, I'd like to, with folded hands, thank all my participants. And I assure you that if all goes well, we will meet personally in a five-star facility in New Delhi. All right. Thank you. And over to you, Ravin sir. Thank you. Thank you.
Thank you, Mr. Dalvi. Truly appreciate that closing remark there. So, as Mr. Dalvi just pointed out, we are planning to move on to bigger and better platforms in the coming editions. Well, to be precise, next year we're planning to do the Gasification India 2022 summit at Taj, New Delhi in November. Hopefully, the physical event will happen. But for the fact that Gasification India 2021 has had some amazing speakers. We've had some visionaries coming in here to explain what the future can be and what the present can actually be used to improve and get to that future. So, with that in mind, I would like to thank all the speakers out here, all the presenters who've been with us, who gave us their valuable insights, gave us their wisdom, and above all, gave us their time. We want to thank you for that. I would also like to thank all the partners, all the sponsors who made this possible. It was not possible without their undying support and their motivation to keep us going despite the hardships of the pandemic happening, and using the technology in order to express our ideas is never easy. So I really want to commend everyone who came in here to be a part of Gasification India 2021. So that's about it from our side. My name is Ravin Kundu. It was truly an honor to listen to all the speakers here, and we really hope to see you in the next edition. Till then, take care of yourself. And as always, at the Gasification India, we really look forward to the future, more greener, more cleaner, and hopefully more sooner than it should have come in any other way. Thank you so much from our side. As Dr. Dalvi just rightly pointed out, if you have any testimonials, if you have anything to say about the sessions, if you want us to improve in any ways, if you enjoyed the conversations today, anything that you would like to share with us, you can raise your hand.
I think, Ravin sir, I think we have T.S. Venkatraman sir who'd like to share something. I
That's
see him raising
amazing.
his hand. Yes, if you
That's
can invite
amazing.
him on stage, please.
Sir, let me quickly get you on the screen and give you the center stage. So Mr. Venkatraman has been a speaker earlier in the sessions, and of course, sir, over to you.
Yeah, as a speaker in both the sessions, I just thanked Anisha for that session. Then jumped over here, and you're not yet finished. So I'm happy, Ravin, that I can also congratulate you and Dalvi here. Instead of just personal touch, I like the vision in which you're doing it. Many people just do gasification seminar. They do alone waste to energy. These two combining because you have ecological impact when you do the gasification and also energy. So these two are combined. So the waste also should be addressed. And if you can make waste energy, nothing like that. That's what my presentation was. RDF2, SAF. So these things I would like to certainly take it forward. And we should have more sponsors I'll work for you to get more sponsors now. Wish you all the best. Thank you, Dalvi. Once again, please convey my best regards to.
Thank you so much, sir. I think your internet connection just dropped. Mr. Desai, I'll
Actually,
hand over.
I wanted to make some comment with reference with in the presence of Mr. Venkatraman. As I told to the other track, and I think Mr. Khatri is also here. Mr. Dalvi also heard my suggestion. One session next time could be a not a question answer, but something like interview. So Mr. T.S. Venkatraman taking interview of three other experts on a on a fixed subject with the floating matter. One question brings another question, brings third question, and then the whatever flowlessness, the methodology, the sequencing can be created. That could be one of the dream I'm having for the next session. May it be virtual, may it be face to face, interview type thing, and it can cover vast. It could be at the end of the session, but it can cover vast requirement and vast points. Another point, as he also supported my view, that mission energy has grown up now so big, rather catapulted much above any platform or any mere any event and coordination, but they can take role like CII, what is taking. That makes the ear and eye for the industry, for the government. Similarly, for gasification and waste and energy, Mission Energy can put that role, make a complete consortium of the industry, and represent all of us to the government and various ministries, can coordinate between the ministry, can coordinate between the industries. That is my suggestion. That is what I foresee. Thank you.
Thank you so much, Mr. Desai. I'm absolutely sure that the team is noting down the points that you've just mentioned, because we really want to make sure that we can take these conversations forward in a way that they make the most impact possible. And absolutely, we'll try and do everything in our power to get to the point where we hit home with all the hard points that we can. So I'm absolutely sure with the next year's physical event coming in November, we will have a floating session where the conversations can flow more fluidly, so that we can add on to some more beneficial points at large for the society and as well as for the industry. For now, I really thank you for your valuable time and for those amazing comments, Mr. Desai.
And
Thank you
I
so
am become fan of your voice. You have amazing voice and voice modulation also.
Thank you. Thank you so much, Mr. Desai. I truly appreciate you saying that. Thank you.
Thank you, everyone.
Okay, so ladies and gentlemen, I think this brings us to the closure end of our 2021 Gasification India event. It was a virtual event this year, as you can see, and we are hoping to have a physical one next year in November in Delhi Taj Hotels. If things go well and we do not have another wave of pandemic, as Mr. Dalvi pointed out, we will be seeing you physically in the next edition of Gasification India. From this edition of Gasification India 2021, as a host for the Waste to Energy technical sessions, I thank you all for your valuable time. We truly appreciate you being here, and we are looking forward to getting to see you again in the next edition. Thank you so much. My name is Ravin Kundu. It was truly an honor to be a host, and have a fantastic evening ahead.